Can you multiply 2 by 2 matrices? I know you guys have had complex, you've had, you most certainly have had linear algebra, right? Oh, yes, and it was not during the COVID semester, no. So it counted. But you have been doing other linear algebra with me since then, so you should be cured. So -1, 0, 0, -1 is what we get. Of course, you should recognize that as minus the identity matrix, right? So, and if you multiplied two of these, A minus B, B, C, A, times C minus D, D, C, what do you get? You get AD minus BC. I can't do math. AC minus BD, and then let's see, what do I get down here? BC plus AD minus AD minus BC, I hope. And then minus, and then AC minus BD. I think that I got a typo right there. That's not C, D. Thank you. So this is just 2 by 2 matrix multiplication, right? But that's complex number multiplication if you use the, just change notation, right? This is A plus IB times C plus ID is equal to what? It's equal to AC minus BD plus I times BC plus AD. Well, that's exactly how we multiply complex numbers, see? So one thing you can tell students is, well, complex numbers, so because you'll come to a certain class of students who will say, there's no such thing as complex numbers. By your own admission, half of them are imaginary. It's not real. These are horrible, horrible terms. So if you have trouble with a student who's denying the existence of complex numbers, you can say, well, do you admit to the existence of 2 by 2 boxes of numbers? And if they'll admit to that much, then you can say, well, look at ones of this form. And then you can show them that by the matrix multiplication that they halfway understand, that in fact there is this thing called complex multiplication. So you can look at it that way. So so my question is, are complex numbers 2 by 2 matrices? I would say no. I don't think of a complex number as a 2 by 2 matrix. I think of a complex number as a complex number. And I think of a nesting, right? Like, I'll be honest with you. When I think about these number systems, I think about them as n is a subset of the integers, is a subset of the rational numbers, is a subset of the real numbers, is a subset of the complex numbers, right? So think about what you're buying into if you insist that the complex numbers are literally these 2 by 2 matrices. Then you are obliged to tell your students also that natural numbers are 2 by 2 matrices of the form n0, 0n. Right? So the point is, this is a model. It shows that there exists such a thing. And so rather than writing 2 by 2 matrices, we just write things of the form A plus BI, where we agree that when you multiply them, it works like that, right? And when you add them, you just add real parts and add imaginary parts. And that's fine. Such things exist. There's another model of the complex number system just by taking R2 and defining a particular operation on it. And then you can prove that that particular operation satisfies all of the axioms of the complex number system. Now, in terms of their significance, so again, in number theory, we're going to study Diophantine equations a little bit. And Diophantine equations, with Diophantus, these are things we're looking for natural number or even rational number solutions to certain polynomial equations. The real numbers are interesting, again, because they're the completion. of the rational numbers. Essentially, it's analysis entering the game. And the complex numbers are interesting because of the fundamental theorem of algebra, which says that, we can completely factor any polynomial over the complex numbers. They're an algebraically complete field. But all the three last examples are fields. What's a field? A field is a commutative ring with identity such that every non-zero element has a multiplicative inverse. Now, I don't think your abstract algebra did it get to that at the end? It varies. Some course. All right, so that's one of the things I want to do in here is I want to complete your knowledge about rings, fields, integral domains. We'll do that carefully as the course goes on. I'm just throwing those terms out there right now, but we will define. Yeah. So, now. Oh, man. Son of a gun. Time flies when you're having fun, huh? Well.
I was thinking I don't have to have coffee in class. It's like I can get through it.
It's because I haven't done any math.
We would have 4 to 3 hours. Like we had our last semester, we had 4
yes. Thank you. Yes.
So we were going to have a 4-hour class. And I talked to Dr. Rakovich and said we're going to finish after this. Yeah.
I start losing where we start the class.
Oh, it's tough. But Dr. Rakovich will not change his mind on the Tuesday night class for real analysis.
That's the one I was thinking of. I think that's really the only one that I had the last.
So let me, before I bail on this, I want to point out their properties. And these will come as no surprise to you, but so like x plus y is equal to y plus x plus y plus z makes sense. Right? We can either do it that way or this way. X plus 0 is equal to x is equal to 0 plus x. And then for each x, there exists minus x such that x plus minus x is equal to 0, right? So, right, this is, what is this? This is commutativity. Additive identity, which we call 0, right? Yeah. And this is,
Zero identity.
Closure under negation, let's say. You could say it that way. You could also say for each element there's an additive inverse, right? So these. Well, there's an abelian group structure in any ring. But my point here is not about an abstract ring. What I want to point out to you is that these properties are enjoyed by the complex numbers. All right? And therefore, they're also enjoyed by any subset of the complex numbers. In particular, the reals, the rationals, the integers, or the natural numbers, or more interesting things we'll look at. So my point here is that almost entirely in this course, we're looking at complex numbers or subsets of complex numbers. So if we understand the properties of the complex numbers, we can use those and not have to reinvent the wheel and prove those every time. So essentially, this means as we introduce new examples, we can just check closure. We don't have to check associativity every time, which would be really annoying.
We did that.
Multiplication is commutative. xy is equal to yx, right? It's associative. xyz is making sense, right? I can multiply xy first or yz first. And there exists 1 such that x times 1 is equal to x is equal to, of course, 1 times x, right? There's a multiplicative identity. All right. And then what else is there? There's distributive properties, right? Like x plus y times z is equal to xz plus yz. And likewise, x times y plus z is equal to xy plus xz. And there's some other things, like minus x is equal to minus 1 times x. It's not at all obvious that the multiplication by minus 1 should be the same as the negation in a ring, but it is. This is actually something you can prove for an abstract ring. That is true. 0 times x, and that's the kind of thing we might run into at the third part of this course when we study abstract algebra just on its lonesome. That's where we'll maybe see homeworks that are proving things like this as possible. I'm going to try to keep it more concrete. I mean, I'm not trying to drag you into the study of abstract ring theory in the first third of the course. The first third of the course should mostly be about the integers, primes, divisibility, and then congruence, how to work with congruence, ultimately leading to actually encryption. So the last topic we'll cover before test 1 will be RSA encryption. And to do encryption, we actually just need to have a really solid grounding in modular arithmetic calculation, which we'll get to. Now, the thing I wanted to end class here with is the construction due to Diophantus some time ago. So this is my, what you're looking at right now is my homepage. And I'm sorry I'm behind. I usually have a announcement put out to you guys before the course starts, and I'm still somehow behind. I don't know how it happened. I blame Audric. It's not your fault, Audric. It's not really fair, but it's convenient. Let's see here. I mean, who else am I going to blame? I guess I blame Caleb. I don't know you well enough to blame you yet, so all in good time. All right, so yeah, this is my homepage, and so it has, like, here's my office hours, and they're right here. And I'll send you a link to this, so just saying it's here. Now, so, notice here I have a link to the course website. So here the previous time I taught it, you know, here's the my mission is just a homework for me. I like Naruto too much. So a mission is, you know, you have rank A, B. Oh, I watch the subtitles. Let's see here. And so here are my lecture notes. So my lecture notes, it's pretty much me just writing out Stillwell and marker and adding some examples here and there. I'm not really following those. I'm trying not to. I'm trying to forge a new path and add value this semester. But on occasion, I'll come back to these. Anyway, lecture 1, though, I wanted to look at. Because in lecture 1, I had written out what's in Stillwell. This is just directly from Stillwell, but Stillwell shows us the, come on, I want to be full screen, you know? Nope, that's not it.
Better.
I guess I'll settle for that. Can you, man. No. That didn't help. Go away.
Try present.
Present.
Yeah, back where you just were the 3 little dots.
Ah, thank you. That's better, I guess. Come on.
Is it not zooming now?
It will not let me. How? Can you guys read it?
I can read.
Or,
Load up actually from my computer.
man, I tell you what, it just aggravates me. So I guess I'll have to settle for this for now.
You're on lecture 1, right?
Yeah, lecture 1. So Diophantus solved this Pythagorean triple problem by instead of looking at this, it basically says, okay, so if you can divide basically by, you're looking for non-zero solutions, so like here, so just divide by c. And so you're really just looking for a over c squared plus b over c squared equal to 1. So you're looking for rational solutions to this simpler equation. Geometrically, this is very nice because it's just like x squared plus y squared equals to 1, right? So you're looking for something on the unit circle. And you're also looking for something on the unit circle with rational coordinates. So like I said, Diophantus he's looking for, he finds a way of solving integer problems by looking for rational solutions. And so basically, he just goes, okay, so you can go from this point to that point, and its slope, because these are both, because that's a rational point, and that is, well, that's the point minus 1, 0, it follows that the slope also has to be a rational number if you think about it. And so you can write the, let's see here, that point r, come on, fail me now. This point r has coordinates x, y, and that y has to be given by, t times the x plus 1 given the geometry here. And then you just do a bunch of algebra, basically. In the algebra, we could understand if I just had allotted 10 minutes to do it, but here it is. So you saw x squared plus y squared ends up giving you that equation in x and t, and then it gives you this, and then that happens, and after a little bit, you have a square, and so that gives you that x plus alpha squared is equal to beta squared, so x is equal to minus alpha plus or minus beta, where alpha and beta are implicitly defined above. And so lo and behold, we get the rational point has this form for t, and continuing on, let's see here, he sets t equals to v over u, and you plug it in, and we find our way back to, after a little bit of further chicanery, we find our way back to the formulas that Audric mentioned earlier in class. So like, you can derive these things in this kind of way. Now, this is not how we'll do things in here. This method, it doesn't work for some of the problems we work out, and I'm more focused on a different method. That's part of the reason I'm not really doing this carefully and slowly. But if you spend about a half hour, you can work through it, and it's nothing earth-shattering. But what is really interesting is how much easier this becomes when we use Gaussian integers. That we will do in class a little bit. After test 1, like up till test 1, we're looking at divisibility and congruence. Like next class, we'll talk about, you guys have Euclidean algorithm? The division algorithm?
Oh, yeah.
So you've done that? Okay, so I'll review it. Make sure we're on the same page. Oh, yes, yes. But this will be, it won't hurt. You will not be bored. So hopefully we'll build up the theory of divisibility, and then that naturally leads to the discussion of modular arithmetic, and so forth.
But yeah, one of my students did the.
I'll stop there.
They showed me the Euclid.
Yeah, now my brother has a handy-dandy web app